So, COMSOL time. We are going to be recreating one of your old samples. Let's do this one. So, we have no image. Let's do this one. We have an image. That's disgusting. Let's do an easy one. I'm sorry. I'm just too lazy. Your samples are garbage.
They really are, yeah. Was there not a complete, like a combined image of the
There was
A1
somewhere, but I can't find it.
Both? Contacts both?
Yeah, that's probably it. Oh, okay, we'll just do this one. Okay, so we're going to make a COMSOL simulation of this. So the first thing that we have to do is we have to turn this shape into a DXF. It's a CAD thing, like a 2D CAD thing. So to do that, we are going to open up this CAD program that I have. You can use any one that you have. This is just free, so I use it. We're going to look for your photo. And we are going to drop the photo in at 0, 0. Photo can really go anywhere, so long as it's in here. So now we have the photo of the thing we want to do. I'm going to go to a new layer. I'm going to call this layer Contacts. And I'm going to select this layer. And now I am going to trace out the contacts. There will be another layer for the sample where we will trace out the sample. Let's actually start with the sample. So we can see that the sample kind of follows this, right? So we are going to now trace that out. The only parts that we care about are going to be between this and this probe. Anything So now we are going to begin tracing out the sample. So this looks like the edge of it, I think.
Mm-hmm. Yeah, that looks about right.
Yeah. It's always hard when it has a rounded edge. I'm gonna just follow along the sample. Then when I get here, I can just drop down to the other side, because, as I said, anything on this side doesn't matter. So this is clearly the edge here, so I can plop it here and continue tracing. And I can trace my way to victory. Looks like it'll go about here-ish. Then we're going to shoot upwards and do the same thing. We want it to match up here. And it looks about straight when we do, so we will. And this is going to be the geometry of our sample. You can play around with how accurate you want it to be, but this is good enough for an educational purpose. Then we are going to change to the contacts layer, and we are now going to trace out the contacts. For this, we care about stuff that is physically touching the probe. So this wire that's coming out, it's not physically touching the sample. So we're not going to trace it. We're only going to trace what is actively touching the sample.
Okay.
So, starting down here might be easiest because it's got a clear profile. So we will I'll just click it back here because that's all it has to do. So we have traced one complete loop for this contact. Every contact that we trace, we need to give it a complete loop. So now we're going to do the same thing for all of these other ones.
For the sake of the video, you could speed up this process, like this whole.
Yeah, I'm gonna, yeah. I know what flies in YouTube space. Angle 2 probe.
Just so you know, these two contacts are not touching, so there should be like the smallest gap in between them. It's difficult to tell where that is, but I know that Sachang had physically like put a scratch in between them.
Yeah, I can see the scratch here.
Yeah.
When I did it, I think I put it about here.
Okay.
I think.
Mm-hmm.
The specific geometry of the contacts is less important than the location of the contacts.
Yeah.
So, yeah, it's pretty obvious, but I just wanted to be clear. If you want to make this easy on yourself, next time you can just, oh god, I'm getting way too in the weeds. Next time you can just take a couple of photos at different lights so you can really tell where the edges are. but it's not my business. It's up to you. I'll make you do the next two. Don't worry. Alright, so you'll do the other two now.
I mean, I think I understand. If you want to keep doing it. It's okay, I'll do
Okay.
it. Okay, it's fine. Not a big deal.
Just remember what I mentioned, how when you... don't include the wire, just the contact.
Okay. Okay. But it should go to the edge, or does it not really matter?
Only put it to the edge if you put it to the edge. I don't
don't
think
remember.
you did this one.
Yeah.
Yeah.
Looks kind of like that. I'll skip that part. I'll kind of skip all the ugly parts.
Oh, when you click on the image, it'll bring it to the top layer. If you click on the image again, it'll bring it to the bottom.
I see.
At least it should. Hit escape. I think you hit move.
Oh.
Contacts. Yeah, okay.
Okay.
You're good. And you
Looks
don't
like
do the
it.
wire, so you can just go around,
Yeah.
like right through it, probably. You can just stick it right in the corner, yeah.
Yeah. Is that
Awesome. So now we are now done with the contacts.
Okay.
One thing that I occasionally do is if there's a lot of junk, what I'll do is I'll add a layer and call it contaminants.
Okay. Ooh. Mints?
I think, yeah, I think that's it. And then I'll select the contaminants layer,
Okay.
and then I'll just
trace them out.
yeah.
Okay.
These can be very rough traces. Like, let me give you an example. Like, if we were gonna like trace these,
Yeah.
it's sufficient to just do this. So, yeah. You can do the other two.
This one?
I meant the one to the top left.
This one?
Yeah, that one. Just make sure it's not touching the main probe. I don't think I saw any others.
Yeah. I
That-
don't know what this is. Just this.
You could do it if you wanted. Yeah, why don't you go ahead and do the tip?
Yeah. This part, right?
Yeah. Yeah, I think that's good. So, now we're just gonna scale it.
Okay.
So,
You want to take over?
sure. To make our lives easier, we're gonna scale it in the software. We want all of these to be 1-to-1 with our sample. So, I'm going to now go to the sample. One of these should have a measurement. That's a bad one. It's the same bad one. Is this the same one?
Yeah.
Yeah, that's what I thought. I thought one of these had a good measurement. It doesn't matter. So, this is good enough for us.
Okay.
We know that the width of the sample is 1,470.86 microns. So now let's just check out what the width of this sample is from there to there. Actually, that photo might tell us if we were in the right spot. Yeah, we were in the right spot. We're good. So, using the measure tool from point to point, we are going to measure the distance of this line, because this is the line we have the measurement for. So, we do the measurement, and in the bottom corner down here, it tells us the distance is 2,792, meaning we need to shrink it by some number. I'm bad at math, so I'm going to use a calculator. and I'm going to divide the number that we know. What was it? 149 something or another. 147.86. I said.
It's not doing anything.
I hit numlock. And we're going to divide that by the measured number that we just got, which is 2792.38. And we find that we need to scale this by 0.567. So what we do is we Control A will scale. Will select everything. So we will hit Control A. This is the modify option. We will go to scale. We will set the origin to the origin. And we will scale it by 0.5267. Good memory. I was going to have to check that. So we do that, and now it should be the same size. Anyway, we're done here. So we are going to save as. I'm going to make a new folder inside Sharia. And we'll just call this the trace. We'll hit save. Cool. So we're basically done with this window. Now we're going to open up COMSOL and we're going to start the funky simulations. This part I will not be cutting out of the video.
That's
The dead silence and just waiting. COMSOL, Model Wizard, 3D. We're going to use the AC/DC electric field and currents, and we want electric currents. We're going to add it, and we're going to study it. So we want the stationary solution. So we're going to hit done, and it's going to give us this window. First thing we're going to do is change the length unit to micrometers. It will save us a lot of mental conversions later. So, in the geometry window, we are going to right click and we're going to make a work plane. So, work plane, we go into the plane geometry, and within the plane geometry of the work plane, we can import our file. So we're going to look for our file, which is in Sharia test trace. So now we get to pick which layers we want to import. We don't want to import them all right away. We're going to only import the sample layer. So selecting sample, we're now going to build selected. This will zoom to the size of the thing. That's our sample. Love it. So we're going to step out of the work plane. And then we're going to build all the objects, and we have the sample. So next thing we're going to do is we are going to extrude this work plane. So we're going to hit extrude, and we're going to say the work plane. And we want it to extrude, I don't know, 500 microns. So the work plane extruded upwards. We don't like that, so we're going to reverse the direction and have it extrude downwards instead. That's just so when we put the contacts on top, it makes intuitive sense.
I think the thickness of this was...
I have the thickness written down.
Okay.
Yeah, so...
This is just for, yeah.
Yeah. So now we should give it the actual thickness as you were talking about. So we're going to go take a look. Oh, I didn't have the thickness written down.
I could probably find it and give it to you. Thickness. Yeah, 220 microns.
So we know the thickness is 220 microns, so we will build at 220 microns. Looks good. So now these two, I'm going to combine them into a group, and I'm just going to call this the sample. It'll just make the whole thing a little easier to look at. And then we're going to repeat the process. Plane geometry, sketch. Actually, I should make you do it. I'll make you do it. Okay, so I can walk you through it if you need.
Yeah. So, right click,
Work plane.
work
Yeah.
plane, and then
To play with the work plane, you got to step into the plane geometry.
okay, and then import, browse.
That's us.
That's open, and then selected contacts,
Just the contacts for now.
and then how do I?
So up at the top, build selected will only build the plane. Build all will just build everything. Both will get you what you want.
Okay. Okay, and then that's it.
Now you have the contacts.
Cool.
So now make the contacts thick.
Then you go to. Oh shit.
You go back to work plane.
Work plane 2.
You just got to build it again.
Okay. So I just do build all objects.
And now
then-
you can tell it to extrude.
Oh.
Extrude is an option that you use.
In the. Oh, here.
It's up at the top,
Yep.
yeah.
Extrude distance. What do you usually give it?
Usually I give it like 100 to 200.
Okay.
Sometimes thicker if they're especially globular.
Did that go down?
The arrow in the middle tells you which way it's going.
Oh, okay. Maybe I'll do 200.
It hasn't built yet. You still have to tell it to build.
And then build all objects. Ooh, maybe I won't do it that much. Like that.
Okay, looks good to me.
Cool.
So, put those into a group also, just so it looks nice.
Yeah.
You gotta select both of them. Oh, I just meant in the geometry, the plane and the extrude.
Okay.
Yeah.
Oh, okay. This and this.
So then you right click. That's weird. That's weird.
Maybe I should take over.
Anyway. Oh, you were doing shift because you're an Apple user.
Ah. Yeah.
Yeah, on Windows it's control.
Oh, got it. Okay.
So, we'll go ahead and add the contaminants as well. I can do that real quick.
Okay.
Won't make you suffer.
Was there an error?
I didn't select them
Oh.
when I was extruding. Usually the contaminants don't play that big a role. I think that's how you spell it. Usually they don't, but it doesn't hurt to have them. Well, it does hurt a little, but we'll get into that. Okay, so now we have the geometry. Let's go ahead and save before we break anything. So, now we have the geometry. The next thing we're going to do is we are going to give the material properties of everything. The easy way to do it is in materials. You can browse a material, and you can just get anything you want. The contacts are made of indium, right?
Woods metal.
Woods metal. I do not remember what conductivity I used for woods metal. Oh well, we'll make it up. So, in materials, we'll right click and we will just create a blank material. This material is going to be for the contacts. So, anything that's purple is what is selected. We don't want the bulk, we only want the contacts. So, right now, just the contacts are selected, we're good to go. The permittivity is 1 because it's a conductor. And the conductivity of woods metal, I forget. It was something though. It was like 1e to the 5. Who knows? But it's something.
Do you have that saved somewhere? If I go to your old simulation for this?
I don't remember if I saved it as wood metal. I'll go take a look real quick. User defined library. Nope. Do not have it defined. If you go there, you can find it though.
Okay.
We could probably do it now, but it's recording.
That's okay. That's okay. We can do that later.
So I'm just going to call this material contacts. And now I am going to do another blank material for the bulk. I'm going to select the bulk. I'm going to give it a permittivity of 1 because it's also a conductor. And this conductivity I will call 1. So I just give it a number right now to satisfy the requirement that it needs a value. So right now materials is happy. Moving on to electric currents. This is the physics portion. By default it gives a bunch of stuff like this. By default everything has current conservation, insulation, and no voltage from the get-go. What we are going to do is we are going to define a ground plane, and we're going to say this one's ground.
Let me confirm.
The other one, wait,
Yeah, no.
do I have it backwards?
This is ground.
This is ground.
This is the source.
Sounds good.
Yeah.
We're going to say this one's ground. And now we are going to look for terminal. We're going to say this one is the source. I give it a input current of 1 amp. That will cause a constant 1 amp of current to flow through this thing. Just because then the voltage maps directly onto the resistance. Saves me a step in the analysis.
Okay.
And then we are going to the mesh section. The mesh section turns everything into little triangles. We're going to see if normal element size works. Build all. Normal does not work. It is too coarse. So where's the error? With you, here, oh, we can't have that. So because we have an abundance of computing power, I'm just going to bump it up to finer. See if that does anything. Finer seems to fix it. Okay, so now it's a bunch of triangles. And what we can now do is hit study. So we're going to study how it looks if this has a conductivity of 1. Looks as you would expect it. So now we're going to study the material, and this is how we will find out what the geometric factor is. So in parameters at the top, we're going to define the resistivity parameter, pxx, and we'll just give it some value. And then in the material property, we're going to go to the bulk, and we're going to set the conductivity equal to 1 divided by the resistivity, because they're inverses of each other. And in study, we're going to do a parameter sweep, and we're going to sweep pxx from 1 e to the minus 5 to 1 e to the 5, something like that. Like, this is when it's about the same as the probes. This is when it's very, very resistive. And 1 step per decade should be good enough for us. So then we are going to compute this study, and it will probably take a hot sec. Do you know why scarecrows get so many awards?
Why?
They're always outstanding in their field.
Did you get this from your the
This?
Yeah.
Found it in the basement.
Oh.
It was given to me in the basement. I did not find it and plug it into a computer. I'm just going to put that out there. Awesome. So we're done with this. Now we've got a bunch of data. So let's go harvest it. So in derived values, we're going to right-click, and we are going to select the surface average of this guy. We're going to pick this surface here because this is the contact. We're going to call this, what probe did you call it? 5? 5. I call it probe 5. And in expressions, this is where we tell what data we are collecting. In expressions, we're going to go to electric currents, electric potential. Replace the description to probe 5. And we're going to hit evaluate. And what this has done is it has evaluated what the voltage is at all the different steps. You can kind of see a pattern. And we're going to do this for the other two as well. I'm hitting duplicate because I'm lazy, but I can't seem to do it right, which defeats the laziness. So what's this probe?
12.
Probe 12. What's this one?
That one is 8.
Probe 8. Okay, so now we want to put it into a table. It coincidentally put them all in the same table, but I'm going to teach you how to do it anyway. So let's make a table, and we're going to call it the voltages. We can call it anything. We want this table to be stored in the model, that means down here, and on a file. And that file is going to be called data. I'm a creative man. So probe 5, we're going to have it evaluate. Hitting the arrow, you can drop down to tell it to evaluate to voltages. Likewise. Likewise. So, in derive values, we can right-click, clear and evaluate all. That'll just reset in case there was any messiness in the table. So now we should have a CSV file called data that has all this information in it. Let's see if we do. Look at that, we do. Data. So now we just need to analyze this data. Obvious source is to use MATLAB. So I'm going to make a new MATLAB script. I'm going to call it going to save as. Going to put it in test. So, collect the data. Sweet, it worked. Get the resistivities. Get the voltage at, what was the first one? 4? 5. 5.
Yeah, 5.
I know it's very enthralling to watch someone else code.
It's okay.
I just want to get this done. Cool. So now if we plot pxx and v5 minus v12, we should get the straight line we so desperately desire. We have this line. We desired it, we got it. So now, if we... So now we want the slope of the line. You can graph it on by doing a fit thing. PXX So, there you go. The geometric factor is roughly going to be about 1.72. Yeah, something like that. Let's double check if the back of the envelope calculation matches. Hopefully it does, otherwise I'm a fool. So the width is... Hey COMSOL, do the math for me. Alright, fine. You do the math for me. So, we said the width was 147 something or another?
1470.86 or something.
Yep. And we know the height is 220.
Yeah, and then the length, which is the length between the two probes.
Length between these two.
Yeah.
So we'll do from about the middle.
Okay. I thought it was edge to edge, no?
If we do it by the center, then the graphs that I do look nicer. But it's the order of magnitude that we care about.
Okay.
So the distance is about 870. And the estimation should be about 2.7. I dropped a 0. Let me just go back and fix that. Yeah, so the estimation is like 2.7 microns. That geometric factor. I can't remember which way the units go. It's like 1 over meters.
It's, yeah.
Yeah,
1 over.
so the estimation should be, and the real value was
1.7.
1.7. Yeah, but that's from center of mass. So the point is it's within like the same order of magnitude.
Okay.
I bet if we did it like point to point, it'd be a lot closer. I'll try it. 260. Let's see if that's any better. It's a lot worse, actually.
How worse?
It comes out to 800, which is far too less. So it's somewhere in the middle. Well, either way, that's what the simulation shows. And we can see.
Is there something that we did that would, if we adjusted something, that it would bring it closer to the estimated value? Like if we made something finer, or like the step size smaller or something?
If we used 0-point contacts, we would get to the correct value every time. there's like so much messiness because for one, it's not even touching the edge. But yeah, the samples, they're very lopsided, non-uniform, things like that. Like you can see if you right click in the results section on one of the cubes, you can give it a contour. You can see for yourself how they like to bow around. I like to give it about like 40 contours. So once they become conductive, they really mess with the voltage profile through the sample. One thing that probably would make it more reliable or similar is if we don't give it such a low resistivity that it's similar to the contacts. If we just keep it like, if we just do like 1 e to the minus 2, stop at 1 e to the 5. Because when the contacts and the probe are about the same conductivity, that's when these guys have much less of an effect on the probe itself.
Okay, so you just did XX.
Yeah.
How does XY work?
Okay, so now we want to do XY. That's going to be hard to explain quickly, so I will explain slowly. I do not know how to do magnets in COMSOL, but I do know how to do resistivities, and that's good enough. So, a while ago we defined PXX, now we're going to define PXY. In the bulk, we have defined the electrical conductivity as that value. Well, we can actually edit the entire 3x3 matrix. So, you probably remember from Louis' class how you can get a conductivity matrix that looks like this. Well, you just make the whole 3x3 matrix, and this will do the Hull stuff for you. So, if we keep PXY as 0, then we'll just get the same thing we got before. But if we don't, then we get spiciness. Yeah, it's still there, okay. So, let's set PXX to be like something conductive, 1 e to the okay, so if it's to the minus 3, the resistance to be on the order of like 1 or 2, so 1000. Okay, we're going to set resistivity to be 1 e to the minus 3. And now we're going to sweep PXY.
Okay.
So you got to keep PXY less than PXX because physics exists. So we're going to go from 1 e to the minus 4 to 1 e to the minus 4. 1 e to the minus. Like we're going to do a negative to positive sweep. And we can give it a 1 e to the minus 5 step size.
Okay.
So we more or less do the same thing. Though before we continue, I'm going to make a new table for Hall. Just because I don't want the old data to get overwritten. we will hit compute. Oh, right, something I always forget to mention. So when you do a parameter sweep, like I'm doing here, there's different parameter types, sweep types you can do.
Okay.
One of the sweep types that it does by default is specified combinations, meaning that if there's the same number in each, it'll only it'll match them up and do that. We want all combinations.
Okay.
So we do this, and we just wait for it to finish. Anyway, once it's done, well, you know where this is going. So once it's done, we can see the magnetic field have an effect. That's good. That's what we like. Drive values. All these are already set up to go into Hall. So I am going to clear and evaluate all. And here we go. Looks good to me. So now we're going to go to MATLAB. We're going to do the same thing, except we're not going to make it log. We're just going to do a normal plot. I'm going to read in Hall data. We want PXY now, not PXX. You are correct. I was the fool. So we're going to want Hall, which is going to be 5 and 8 now.
Also, is it really all 5 columns?
What?
So you have, they're not in the same, like the PXX, PXY, they're not in the same CSV.
Yeah, they're in a different CSV.
Right.
So the different CSV that we just made, Hall, it has these columns.
Ah, okay, yeah, never mind.
Okay, so polyfit. You want to keep polyfit? R5, 8. And we're going to plot.
It should actually be not 5, 8, it should be 8, 12.
8, 12?
Yeah.
Okay, all the same. Thank you for the correction. Let's see some good numbers. Yeah, numbers look pretty good. Beautiful.
Is that what it was last time?
No, last time it was the other way, and it was a much different magnitude. Though the polyfit is way off because I did XX instead of XY.
Oh, that would make sense. There it
That
is.
looks better. Yeah, so the slope is usually what you want, yeah? Okay.
Yeah.
So, back of the envelope calculation, it should be about 1 over the thickness, ish, right? The thickness is
220 microns.
220. So we want 1 divided by 226, which should be about 4,500. It's 1,500. It's close enough. It's the order of magnitude that matters.
Okay.
So this is the hull slope.
So
We can get more accurate if we like do anti-symmetrization and stuff, obviously.
You say RA12 is equal to the difference between the two voltages, but I mean you say R, but it's actually just V.
It is.
Right? It's in volts.
It is V, but amps is set to be 1 amp at all times.
Okay, so it's
So
always gonna just
that's
be...
why I just set it to be 1 amp. Is because doing the conversion is annoying. So I just.
Got it. Okay.
But you are correct that
Yeah.
it is. It's actually V.
Okay.
Yeah. So that's basically how you do magnetic stuff. You already know this, but I'm going to say it anyway. The more accurate you do a simulation, the more accurate your results will be. It's often a good idea to experiment with smaller probes just to see if you approach like the ideal value, just to make sure. But yeah, that's pretty much it.
Okay.
And you can get pretty pictures in the results section. Just do a plot group. For the plot group, you can give it a volume surface. Delete the table. Make it watermelon. Yeah, that's basically it.
Cool. Can you also show how to do the surface stuff for SMD6? Since that is something that I will be taking once Dimitri leaves.
Yes. I'm probably gonna make this a new video though.
Sure, that's fine.
And done. Hope this was recording. Oh, good.